Martin, who, as it says, is a member of the particle theory group at University of Plymouth. Yeah. See? I shall pass you over to Martin.
Sit somewhere else.
That's the keyboard
It's
now.
sticking. You have the pillar in the way. Yeah.
How it's falling on the floor. The key is falling on the floor.
Technology, I'm not very good at it. Okay, well, thank you, Gary. So my name is Martin, and I'm a mathematical physicist based at the university just up the road. And Gary asked me a short while ago if I'd be happy to come and give a talk to you, and of course I said yes, I'd love to. And then, of course, having said that, you think to yourself, oh my God, what am I going to talk about? And so the first thing that I thought was, you know, do I have to give a talk about sort of the physics of science fiction or something? But first of all, you know, there's books about this, and secondly, most of those things tend to be sort of critical on the lines of, you know, you can't hear a photon torpedo going through space, but I mean, you know that anyway, don't you? I mean, you know, an alien's going to space, no one can hear you scream, so they can't hear you firing a photon torpedo either. And it's a little bit cheap to do something like this anyway. So I had a chat with Gary, I had a beer with Gary, and he said, no, you can just talk about science and maths. And I thought, okay, that's great. So I'll talk about science and maths, and I'll try to occasionally have a little bit of relevance to science fiction, and hopefully it's fun as well. So, what do I actually hope you get from this talk? Well, it's a big universe. I mean, I'm sure you all know that already, but you know, we'll try to use a few numbers about it. And these numbers are going to be very big numbers. So part of the talk, I'm actually going to be just discussing what big numbers mean and trying to give a feeling for the differences. Sort of a feeling for the differences which, as we know to our costs, various people, including bankers, don't seem to understand. I'm also going to be talking about some surprising things, and I think one of the most surprising things I'm going to talk about is this idea of growth, and exponential growth. So there's going to be a bit of the talk about that, and I think that is a really important thing for people to understand. And the talk's finally going to conclude with some ideas about pressure, the physical concept of pressure, and also some ideas about colour, why it is that, for example, your t-shirt is red. Okay? So that's the idea of the talk. So this is one of my favourite pictures. It's a picture from the Hubble telescope, deep view, you know, looking really far back into the universe, about as far away as we can see it. And so is this in your way?
No.
Let's see if I can pull it. So this is the Hubble telescope view, and all these sort of dots here, these quite large dots, each one of them is actually a galaxy, not a star. Now, here's another picture, again, all dots, galaxies. And we talk about the observable universe as the bit of the universe that we're able to see. And as far as we're aware, this is about 90 billion light years across. And at this stage, I should apologise to anybody who's old-fashioned, you know, the way I would tend to be myself. Whenever I say billion, I mean the US billion. So by billion, I mean 1,000 million. Okay? So it's about 90 billion light years across, which sounds very big, although I haven't said what a light year is. And in it, there are lots of galaxies. This, I think, is a really beautiful picture. It's a thing called a perfect galaxy. It's not our galaxy, the Milky Way. We're in that, so we couldn't get a picture of it like this. It is just a spiral galaxy, like our Milky Way, and by chance, it is at right angles to us. So when we look out at it, we see it at right angles. We see the full disk of it, and that's why we're able to get a beautiful photograph of it. Now, our Milky Way looks a little bit like this. It's a spiral galaxy as well, and it is 30,000 light years across. In other words, it takes light 30,000 years to cross this. There are a huge number of stars in the Milky Way. There are a few times 10 to the 11 stars. Now, what does that mean? It's something I'm going to be talking about a lot. 10 to the 11 means 10 multiplied by itself 11 times. 4, 5, 6, 7, 8, 9, 10, 11. And that is 1 followed by 11 zeros. I should have written 100 there. So it's 10 to the 11 is just shorthand notation. It's obviously a lot easier than writing this out by hand. So 1 followed by 11 zeros. Okay? In words, that's 1,000, that's 1,000,000, that's 1,000,000,000, so it's 100 billion stars roughly. Huge number. Now, how far apart are these galaxies in the universe? Well, the typical distance is much bigger again. There are a few million light years between galaxies. That doesn't mean that they don't crash into each other. That's a picture of two galaxies colliding in space. And if you just put that into Google, you will find other images out there of galaxies that hit each other. So, this galaxy has a careless driver and needs to have its license revoked. So what I've been doing is I've been using lots and lots of huge numbers. And we have to ask ourselves what they mean and what the differences are between them. I've talked about billions, I've talked about millions. We should also think a little bit perhaps about a light year. But a light year is easy-ish. A light year is the distance that it takes light to cover. Sorry, no, light year is the time, and it's light being a year. 1 light year is the distance covered by light in 1 year. Okay. And light goes 300 million meters in 1 second. So in a year, it's an absolutely huge distance. So what are these big numbers? Well, we know about 1,000, 10 to the 3. 1,000,000 is 1,000 multiplied by 1,000, 6 zeros, so it's 10 multiplied by itself 6 times. A billion, again I'm using the American way, is 1,000,000 multiplied by 1,000, 1,000 million, 9 zeros. And a trillion, which is as far as I'm going to go today, and I also start getting confused about the numbers after a trillion, is 1 followed by 12 zeros. So in other words, it is 1,000,000,000,000, or it's 1,000 billion. So it's absolutely huge numbers. Now, at this stage, we can ask ourselves, can we really imagine this? Can we imagine differences between these numbers? I don't think that's easy at all. I don't think normally I can, really. The sort of largest number that you could maybe imagine is perhaps something like a really big sports stadium, full of people. And even if you're sitting in it, you're not going to see all the people there, but that might give you some sort of feeling. So Wembley takes about 90,000. The largest sports stadium in the world is 150,000. Just out of curiosity, does anybody know where this is? I didn't before Friday, I have to admit. Largest sports stadium in the world. Dubai?
China?
It's North Korea. I had no idea myself. I guess it's good for marching or something. So I think one way of trying to visualize these numbers, perhaps, is to think about it in terms of time. So we can think about what is 1,000 seconds. What's 1,000 seconds? What's 1,000,000 seconds? What's 1,000,000,000 seconds? And what's 1,000,000,000,000 seconds? Okay, so to do this for 1,000 seconds, what we have to do is we have to divide it by 60 to convert it into a unit that we can get our head around a little bit more, and that will be in minutes. So we can get rid of that and that. And 100 divided by 6 is going to be a little bit more than 10 minutes, isn't it? Divided by 10, we have exactly 10 minutes. So let's just see what we can get if we're a little bit more exact. It is to the nearest minute, 17 minutes. What about 1,000,000 seconds? Who here thinks they might have lived to be 1,000,000 seconds old already? Yep, you're absolutely right, you have. Okay, so 1,000,000 seconds, what we do is we're going to multiply it by 1,000 to have 1,000,000 seconds, and then we're going to have our answer at the moment in minutes, and that's not going to be good enough, so let's perhaps divide it by another 60 to turn it into hours. So 1,000,000 seconds, we're going to divide it by a bit more, we're going to divide it by 24, and that puts it into days. So 1,000,000 seconds to the nearest day is 12 days. It's a bit more than 11.5 days. So the difference between 1,000 seconds and 1,000,000 seconds is absolutely huge. One is 17 minutes. One of them is about 12 days. Really big difference. What about 1,000,000,000 seconds? Who here thinks they've lived for 1,000,000,000 seconds? Anybody? You haven't. Unless you look really young for your age. Well, okay, so 1,000,000,000 seconds, we multiply by 1,000, so it's going to be 12 days times 1,000, and 12 days, roughly, times 1,000 to have 1,000,000,000 seconds, and then days isn't going to be the right unit anymore, so we'll divide by 365. So you can imagine that's about 3 times 12, it's going to be 30 odd years. And it is 32 years to the nearest year. Is it for 1,000,000 seconds? I haven't either. It's 2 of us. What about 1,000,000,000,000 seconds? 1,000,000,000,000 seconds.
No.
Well, at this stage, I'm not even going to ask the question. Actually, do we have an alien in our midst? Does anybody live for 1,000,000,000 seconds? Cool.
Time Lord over there.
I don't really have a nice unit for it anymore. All I can do is just be a little bit. It's very simple and say, well, 1,000,000,000,000 is 1,000 billion, so it's 32,000 years. And if you want to have a historical event to go with it, that's roughly the time, I believe, when Neanderthals died out. Okay, and I believe humanity has been around on this planet for about 10 trillion seconds. Okay. So the point I want to get across from this is that there is an absolutely huge difference between 1,000, a million, a billion, and a trillion. And I think it's worth reflecting on. If somebody says that that we spent $1 billion or £1 billion, and somebody says we spent £1 million, there's a huge difference between those two. So, by the way, we don't have any investment bankers in the room, do we? Okay, carry on the talk. I don't need to run. Okay. So a lot of people have trouble with big numbers. The US Treasury, for example. In 2008, towards the start of the recession, the US government said they were going to bail out the banks, the sort of thing that's happened here as well. And they had a thing called the Paulson Plan, the Secretary of the Treasury at the time, I think, and they said they were going to put $700 billion in to fix the banks. In the meantime, they'll spend an awful lot more. And the Treasury spokesman told Forbes Business Magazine, it's not based on any particular data point, we just wanted to choose a really large number. Now, another thing that I think one can think about this is how big is big. Whenever somebody says something's big, I think the question you've got to ask is compared to what? So in 2006, the NHS was said to be heading for a £1 billion budget deficit. Exactly. There was a big fuss about it in the media. And the question I asked is, did anybody cared at all? And your answer is?
I've been working in the NHS now a whole lot of years, and I'm surprised that's not actually difficult.
It's not big. The NHS budget is of the order of 100 billion. I've got to find this button again. It's around 100 billion. So this budget deficit was about 1%. Now, I mean, getting your budget right to 1% is really good. Very impressed by it. So, whenever we ask ourselves, how big is a big number, we should do that. Now, I've stolen this example from a book which I would recommend to anybody who's interested in these things, called The Tiger That Isn't. I'm absolutely sure that there is no other book called that. So if you're interested in reading a little bit more about sort of statistical applications and very surprising stories, I think it's a joy to read. You know, I think it's a book to read just for fun. That's a story in it, and the very first story, I don't want to offend many of you, the very first story actually points out that the Daily Mail scale is wrong. The Daily Mail scare is wrong as well. So, I hope not offend too many people with that comment. I think that's a really good book to read if anybody wants to look into this. Okay. So after that, what I want to do now is I want to talk about exponential growth. We hear an awful lot of talk about economics, for example, about growth and growth rates and so on, and it all revolves around this equation. I'm going to talk about the equation in a moment. And I actually have been told of people getting jobs with banks because they knew that equation. You know. So this is, what it means is the following. If you have something which starts at P, so let's just put something in the numbers. So let's imagine that we're going to be positive, cheerful, happy people. We're going to invest rather than have debt. Let's imagine that we start off with £1,000. And let's say we find a really kind bank that says they're going to give you 10% interest. It makes the sums easier, so that's what I'm doing. So then, at the beginning, you have £1,000. And after a year, you have £1,000, but you also have 10%, so 10 over 100. So that's this n over 100 written over there. And then if you were to leave it, so this would be after 1 year, that's the amount of money you have, 1. But if you had it for 2 years, and I'm not going to prove it, but what happens is you square that. If you had it for 3 years, you would cube it. So if you have it for t years, you multiply it by itself t times. So that's all that equation means. So it would be 1,000. So let's say after 7 years, you'd have £1,000 times 1.1, because that's 1 plus 10 over 100, multiplied by itself 7 times. Okay? Yeah, I would be too. So this is the equation which basically describes your mortgage. It's the equation which describes your pensions, everything like this. So it's a really, really key equation. We're going to talk about it quite a lot. There's a rule for this, which is a really nice rule to know. And again, I'm not going to prove it. And the rule is that if n isn't too big, and again, what does big mean? Big means compared to 100. And let's face it, we're not going to find a bank that gives you 100% interest rate or anything like that. So then it's going to double every 70 divided by n years. Okay? So if you had 7% interest, what you invest will double after 70 divided by 7, in other words, after 10 years. Okay? So if you find a bank that will give you 7% interest, whatever money you invest will double after 10 years. Okay, so that's the equation, and that's a useful fact, and we're going to use both of those things as we go on. As I've said, this is the key equation of capitalism. It's the equation which all of the financial systems use and are based on. It's also how populations, humans, bacteria, whatever you want, grow according to this equation. So it's what happens with petri dishes, it's what happens with populations. And I think it's very badly understood, and it has huge implications. And if you want to look into this a bit more, if you go onto YouTube, there is a lecture by somebody in Colorado, which I think is an absolutely wonderful talk. It's split into 8 bits, so you have to watch them bit by bit. And it has the slightly immodest title, the most important video you will ever see. So if you put that into YouTube, you'll find it. And I think it's a wonderful lecture. I paid him the compliment of buying his book after I'd seen the lecture. So to give an example of this, I want to talk a little about exponential growth. I want to talk a bit about doubling. So the equation we had a moment ago is this one here. So imagine that n was 100%, and again, you're not going to get it from a bank. You'd have 1 plus 100 over 100, you have 2. So every year what you'd have would double. Okay? So let's take an example of doubling something to get an idea of how this works. What I'm going to double is this sheet of paper. So imagine if we fold it, it's twice as thick as it was. Fold it again, it's 4 times as thick as it was. Fold it again 3 times, it's now 8 times as thick as it was, etc. My question to you is, how often do you need to fold a sheet of paper? If you're worried about folds, we can just tear it. Okay. How often do we need to tear it until it is taller than a house? Okay. And I don't care, it's just a rough normal house-ish. So, and if you want to know, the thickness of a sheet of paper is typically 1/10 of a millimetre. So and we're ignoring air trapped between the sheets and so on. So 10 sheets would be a millimetre thick. So would anybody like to have a guess? Just a number. 150? Who thinks more than 150? Few people? Who thinks less than 150? Who's not sure? Okay. Well, it turns out that the answer is 17 times. Okay. So 17 times you would have a pile of paper taller than a house. Now, I'm not going to go through all of it, but I'm going to show you roughly what it is if you were to do it 20 times. So what we're going to have to do is multiply 2 together. So 2 multiplied by itself once. So I used to do this on whiteboard, so I was trying to wipe this off. So 2 to the 1 says just means 2 once is 2. 2 squared is 2 cubed. 8. 2 to the 4th. 2 to the 5th. 2 to the 6th. 2 to the 7th. 2 to the 8th. We're going to do it 3 more times. 2, 5, 6. 2 to the 9th. 12. And 2 to the 10th. 10, 24, 1,024, which is pretty close to 1,000. Okay? Now I'm going to be very lazy. I'm going to say it's 1,000 because I want to get a rough idea. Also, I don't know how tall the house is. Thickness of the paper is probably not exactly the same. If you multiply 2 by itself 10 times, you have 1,000. Okay? And I think that's a number we're going to be coming back to as the talk goes on. So, supposing you had to multiply 2 and you did it 20 times. Well, that means you multiply by 2 10 times, and then you multiply it by 2 another 10 times, don't you? Agreed? You multiply it by 10 10 times, and then another 10. So that's going to be 1,024 times 1,024, which is roughly 1,000 times 1,000. Roughly. So it's roughly a million. So if you were to take a sheet of paper and tear it in half and double it this way, 20 times you would have over 1 million sheets of paper piled up. Now, 1 sheet of paper is 1/10 of a millimetre. So if you do it 1,000 times, you have 1,000 times 1/10 of a millimetre. But a millimetre is what part of a metre? It's 1,000th of a metre, isn't it? 1,000 millimetres in a metre. So we can get rid of the 1,000 and just say we have 1/10 of a metre. Now if you did it another 1,000 times, so times, so a million times, or in total, we'd have 1,000 times 1/10 of a metre, so that would be 100 metres tall. So if you take a sheet of paper and you tear it in half and double it 20 times, your sheet of paper, your pile of paper would be over 100 metres tall. Okay? Which is shocking. And this is what happens with exponential growth. You think 2 times, 4 times, 8 times, whatever. It's not so big, it starts somewhere, but after a while it starts to go like that. And this is why lots of things happen. It's also why credit cards work, because they charge interest based on this equation. And let's have a look at a nice credit card, not a nice one. There was a survey of UK credit cards a few years ago, and the most expensive one turned out to be the Capital One Bank Classic. I love the word classic there. It's obviously, it sounds good and safe, doesn't it? It's actually not nice at all. It charges 34.9% interest. So this is our equation, key equation of capitalism. And here we put n as 34.9. So it's 1.349, etc. So let's just have a table. You owe £1,000 on this card. What happens? After 1 year, you owe them 1,349. That's 1,000 times 1.349. After 2 years, you owe them £1,820. And I'm assuming they're nice, kind bankers who don't put charges on and just charge the interest. This is wrong. 5 years, you owe them almost £5,000. 10 years, 20. 20 years, you owe them getting on for £500,000. Okay? Isn't it shocking? This is this happening. Now, oh, by the way, do you remember we talked about doubling? I'm going to talk about doubling again in a minute. And we said that the doubling time is 70 divided by the interest rate, if the interest rate is less than 100. Well, 34.9 isn't that much less than 100, so it's not going to be perfect. But 70 divided by 34.9 is almost 2, isn't it? So after 2 years, you'd expect it to almost double. And you see it has almost. It's not quite £2,000, but it's getting on for it. Okay? So why on earth would somebody want a card like that? Well, one reason is they give you a free choice of card design. And that is one of the choices on their website. I think they were looking in the mirror when they designed that one. But the other reason is that this is the one that they would give you if you don't have much credit. Now I know that this is too hard to read for people far away because it's taken off their website, so it's a fairly low-res image. But you know, who would this one be given to? Well, I've had little credit in the past. I've had an overdraft with no credit cards. I've had credit problems in the past. I have no credit history. For example, I've never used credit. I'm a student. I'm new to the country. So basically, they will give you a card like that if they can. So it's aimed at students, but not people who know something about maths. But I hope you're very, very careful about these things. So just to recap what we've seen before. If you multiply 2 by itself 10 times, you get roughly 1,000. 2 by itself 20 times is 1,000 times 1,000 roughly, so it's about 1,000,000. 30 times is 1,000 roughly times 1,000 times 1,000. It's about 1 billion, 1,000 million. And if you did it 40 times, you would have roughly 1 trillion. Okay? And that's actually accurate to within a couple of percent. So it is actually very accurate. So let's use this to think about a colony. Let's imagine we send a spaceship to a planet, and it's got some colonists, and let's see how they're going to grow. So we've got 300 settlers on our spaceship. We couldn't build a bigger one. And we have a population growth of about 3.5% a year. So after 1 year, we would have 300 plus 3.5% of that, which is going to be about 10 more people, 310 people. And 3.5% is not unrealistic, by the way. You know, these things do happen with humans. So 3.5% annual growth, we can work out the doubling time very easily. That's why we chose it. 70 divided by 3.5. And that's 7 divided by 2, so it's about 20 years. It is 20 years. So this will double, the population will double on our colony every 20 years. So after 200 years, you've had 10 doubling times. So you're going to multiply by 2 10 times. You said that's about 1,000. So we're going to have 300,000 people on the planet. After 400 years, we've had 20 doubling times. 400 is 20 times 20. So we're going to have 300 times a million. So we have 300 million people on the planet within 400 years of our spaceship landing. Assuming there's no war or anything. After 600 years, you have 30 doubling times, you've got 300 billion people on the planet. Yep.
You managed that this being capitalism is 2 to the power of 20.
Oh, thank you. It's called copying, cutting and pasting, isn't it? You're absolutely right. It should be 300 times 2 times 2. What about if it was 800 years? Then you'd have 40 doubling times 300 times 2 to the 40. You'd have 300 trillion people on the planet.
So generation shifts generally a bad idea then?
Or you give
Without
them
ZP
contraceptives.
Without ZPG.
Yeah.
Yeah, throw it in the tea or whatever. So this actually, and this is right. This is also how, for example, bacteria are in petri dishes. It's how plagues grow. All of those sorts of things. It's exactly this sort of maths. It's this sort of curve. Now, another example of this is the idea of extracting resources that are not renewable. So, the examples I'm talking about, things like taking water out of a fossil aquifer. An aquifer is where there's water under the ground. A fossil one means that it's not being replenished by rainfall. The water gets into it very slowly over geological times, nothing compared to the amount of time that we're taking the water out of. And these things are very important, and we are taking water out of all the time. Or you could be imagining oil. Oil is obviously being replenished at an incredibly slow rate compared to the rate we're taking it out of the ground. So let's imagine that we take some amount of oil out of the ground. I've no idea how much it is. It could be 1,000 barrels. You know, in our first period, I don't know. I don't care. Just some amount. Whatever it is, if we continue growing at this way, using exponential growth, which is what people mean when they talk about the economy growing at 5% or whatever, then during the second doubling time, we're going to take 2 times out. So if we've taken 1,000 barrels in the first time, in the second time we take out 2,000 barrels. In the third doubling time, we're going to take out 4 times, so it would be 4,000 barrels. I think you can see the pattern here. Next one we take 8, the one after that we take 16. So this is just doubling again. The point about it that I want to make you realise that's very surprising is the following. The first one is sort of obvious. In the second doubling time we take out more than in the first. We take out 2 times whatever we took out in the first one. In the third period we take out 4. And that's 4 is more than 2 and 1 together. So in the third doubling time, we take more oil or more water out than we've taken out during the first 2 periods together. In the next one, we take out 8, and 8 is more than 4 and 2 and 1. In the next one, we take out 16. 16 is more than 8 and 4 and 2 and 1 added together. So if something is growing exponentially, in any doubling time, you use more than all previous history put together. So supposing you're taking something out at 7% growth rate, then the doubling time is a decade, and it means in any decade you take out more than you've taken from all previous history. And I think things like this is going to be important for a lot of science fiction, which you know probably much better than I do, about things like shortage wars and things like that. I'm sure there's such stuff out there. Okay. So that's the mathematical side of it. We've talked about large numbers and we've talked about exponential growth, both of which I think are very, very important to understand. The rest of the talk, I want to talk first of all about pressure, and then I want to talk about colour. So pressure, we're all under pressure all the time. We have air on top of us pushing down. I have this picture of the son of a friend of mine who's very, very brave with all these arrows snapping into him. It's not called Sebastian. So we all have air pressure on us, and if you recollect Total Recall, when they pump the air out in Arnold Schwarzenegger's face. At sea level, it's like having a kilogram piled on each square centimetre, if I got my maths right. And the question I want to ask is, can we demonstrate it? The answer is yes, we can, but we might make a mess. So, I'll try and do it here on the table so that you can see it. If you're behind the pillar, you may need to move a little. And if you do this, please don't do it on top of the carpet or furniture or anything like that, but do it on top of the sink. Okay? So we've got some water in the glass, just normal water, beer mat, and I'm going to turn it upside down on top of the thing. Now, we have air pressure here, pressing at the beer mat. It is also underneath pressing up at the beer mat. The air pressure is holding the water in place. Had to happen eventually. So that's air pressure on all of us. This is used in science fiction, of course, in spaceships with solar sails. Spaceships that are propelled by light hitting them. And there's different versions. It's either the light from the sun, radiation pressure, or it could be a very powerful laser. There are ideas of having lasers on the ground, trained on a disappearing spaceship, aimed at them and so on, making them move away. And actually, the Japanese this year have sent off the first solar sail-powered spaceship. And it's called Icaros. I forget exactly what all the letters stand for, but I do know the letter K stands for kite. Let's hope it stays in the air. So this image is just taken from their website, and for the mission, it's in place as we speak at the moment. They've deployed the solar sail, and it is trying to go towards, I think, first Venus and then onto the Sun. So if you want to, you can just put Icaros or solar sail Japanese spaceship, and you will find the webpage of the mission talking about it. And what I'd like to try to show you is that we can actually demonstrate this idea of a solar sail. And we're going to have, there was a flash in some switch here. There you go. So switch the flash on again. And here I have my solar sail. The solar sail is a mirror, a symbol. Whoops! Sorry, it's there, sorry. Is the microphone on? I think it is. That wasn't the flash. Now, you may not hear this, and if you don't hear it, what we can do is we can do it again after the talk's over. People can come up and hear it.
If you're very quiet, you should be able to hear it.
If you're very quiet, you don't hear it, try not to mention it. So here it is. Here's a flash. You need a fairly powerful flash, and it's much better if it's at the side. So we're going to flash the light hits the symbol, and it knocks into it. That's the idea of the pressure of a solar sail. It is hit by the light. It is pushed. So here we go. Anybody hear that?
Yeah. Come closer if you can't get it.
Or we can do it at the end. We'll do it at the end. But we'll do it again at the end of the talk. So we can do it as long as the battery. Thank you very much for the flash, by the way. This flash is.
Thanks. Wave luck.
Thank you. So if you want to, we can I'll switch it off again. If you want to, we can do it again. You can come up and hear it close up after the talk's over. That's how the solar sail works. Light hits it, it knocks it. And I must admit, when I first read you could do that, I thought, no, you can't. But you can. Okay. What about pressure? A bit more about pressure. One of the things it can help us do is it can help us design our alien monsters. So, I'd like to show you a little video.
More than 4 metric tons, averaging 19 feet in height, creature was believed to be one of the largest predators who ever lived on the planet.
So, I really like the Godzilla film, but I think they have to redesign Godzilla a bit, and I'm going to try to explain why. Okay. So, Godzilla there looked pretty much like a T-Rex, which was scaled up and made bigger. Do you agree? Yeah. So that's the problem. Let's imagine that Godzilla is 20 times bigger than a T-Rex in every direction. I've done that because the numbers are easy. So that would mean her volume, 20 times taller, 20 times wider, 20 times more thicker that way. So her volume would go as 20 times 20 times 20 larger, which is 8,000 times larger. So assuming she's made the sort of stuff that we're all made out of, her mass would be 8,000 times larger. But she's standing on legs, and her legs look pretty much the same as our legs. So what you have is you have pressure on the legs. That's a very simple picture of Godzilla's legs. And the pressure is her weight pressing down through this area. And the area is 20 times bigger. It's 20 times bigger that way, 20 times bigger that way. So the area is going to go as 20 squared, which is 400. So the weight is 8,000 times bigger, but the pressure, but the area is only 400 times bigger. So the pressure, which is force over area, is 8,000 over 400. It's 20 times larger than the pressure on the legs of the T-Rex. Now, this, of course, is why when you go out onto ice, you don't put your stiletto shoes on, but you put your snowshoes on to have less pressure on the ice to make it break less. This is why Godzilla would not be able to stand up, her poor legs would break, and if you're going to design an alien, well, not, she's not an alien, if you're going to design a monster like that, will have much bigger legs. So I've taken a couple of photographs off the web. One is of a moose, and one is of some sort of little gazelle creature. And I've just done a very, very cheap, simple thing to do it. I've taken the image here, and I've scaled it up with an image editor to make the body look about the same size as the body of the moose. And now what we do is we look at the legs. And what you see is that the legs of the moose look bigger, even when the body of this thing has been scaled up, than the legs of the gazelle. So if you've got a gazelle and you want to make it really big, put it on steroids and so on, you're going to have to make its legs bigger. So that otherwise it will be lying on the ground unable to run. So anybody who's trying to design a huge monster, I think this is something to bear in mind. You've got to make really, really big, chunky legs.
Yeah.
So, we're going to talk a little bit about colour. We're going to ask ourselves the question, why is a red shirt red? Yes, Jamie. Now, the thing we know about light, the whitish light around us in this room, is that it's a mixture of different colours. You put it through a prism, it splits up. We've all seen the Pink Floyd Dark Side of the Moon album cover, if nothing else. And so, white light, the light around us that's bouncing off this is actually a mixture of different colours. And when something has a colour, there are two ways that it can have a colour. One is that it absorbs some light and only reflects some of the other, and the colour that you see is what is reflected, because the stuff that's reflected is what comes into your eyes. Or you can have iridescence, which I'm going to talk about in a moment. And iridescence is what happens if you look at, say, an oil film on the water in a petrol station, or more nicely, if you look at a bubble, or if you look at the throat of a hummingbird, or the wings of a butterfly. And it's also used in some modern technologies. So, what's iridescence? Iridescence is quite different to absorption. So, we think of light as being made of waves, and supposing this is a bubble, what can happen is that the light comes in and it can either hit the front of the bubble and reflect off, or it can go through the front of the bubble, hit the back and bounce off there. Now, look at this one here that's come through, hit the back, bounced off and come out this way, and this one that's come here, hit the front here and bounced off. Both of those things are going off together. Now if you think of light as waves, like water waves or something, if you've got here a peak with a trough for one wave, a peak with a trough the other way, they're just going to cancel each other out. You wouldn't see any blue light coming off there. But if we look at it now with red light, goes through here, this extra distance that this one has travelled is such that here we have a trough and a trough, a peak and a peak. They add together and you get that light, you see that light. So you don't see the blue light here, but you do see the red light. Now you can imagine perhaps, let me just come around here, that if we were looking at light that reflects off this way, it's going to travel through a different distance of the bubble. Can you imagine that? So that would mean if you look at it at different angles, you might see different colours. And this is what happens. So this iridescence is the reason why butterfly wings have pretty colours. Like some of it's reflected off the top, some goes in a bit and is then reflected off. It's what happens with soap bubbles. And actually, if you ever look at a soap bubble, you might notice that shortly before it pops, it actually stops having pretty colours quite often. And that's to do with the fact that the thick is getting thinner, and that thickness for producing the iridescent pattern isn't enough for the visible light that we can see. And it's also used in new technologies. So I've got an example of this in technology to show you. So here we have a car, and I'd like you to shout out loud what colour the car is.
Pink.
Great. Oh, so
Pink.
pink.
Purple.
Green. Yes.
Very expensive paint job.
Very.
Blue again. No one's going to guess why red police, isn't it?
I think there's probably very few cars with this property, I suspect.
Shine.
Good.
Really blue. Pink.
Yeah, we've got more seven.
And I believe, I don't know anything about it, but I believe there is actually makeup available with iridescent built into it as well. So that's I think a nice example. But that's not the way. This is not the way that I've lost the mouse again. Oh, there it is. Well, no. But that's not the way that most t-shirts, unless you have some incredibly high-tech t-shirt, works. What happens with a t-shirt is the light comes through and it hits it, and depending on what the material is, what the dyes are that you use to make it, some of the light is absorbed and some of it is reflected. And the light that is reflected is the colour we see. So a red shirt reflects red light and absorbs other colours. A green shirt reflects green light. So, I'm now going to try to demonstrate this. To demonstrate it, I'm going to try to turn this thing around. Two balloons, and I'm really pleased I didn't keep you on that time. I think those things that I wasn't thinking about it. So here we have a very bright green laser pointer. It's very bright, so you really don't want to shine it in your eyes. Now, to see whether this works or whether I need some get a pin out. What I'm going to do is I'm going to shine it at the green balloon. If I shine it at the green balloon, the green light is reflected off the green balloon. Okay? So the balloon should not be getting significantly hotter where it's being hit, because all the light is just bouncing off it. It's like a mirror. So it shouldn't pop. So far it hasn't. You now aim the green laser pointer at the red balloon, and it's gone. And I've got to now try and hold it, keep it steady, and aim it at a point. Really hoping this is going to work.
Did you ever try it before?
I've seen it done. I don't have a green laser pointer. I had to borrow this off somebody. Actually, with the duct tape, we can aim it and point it at it, stick it on a chair and just sit there.
I can sneak behind with a pen.
Yeah, tape is available.
Yeah, we have got tape.
Or I should have a pin at the end of it. It's a class 2 laser pointer. It's supposed to be really strong. It's a good balloon, isn't it? You get a high quality product if you
Yeah,
buy
it's
it
not
from
McDonald's.
Okay, I give up at this stage. But if anybody wants to have a go, they're absolutely welcome.
Is it getting hot?
It should eventually pop. So, can we demonstrate it? The answer is no.
It worked in rehearsal.
It worked in rehearsal when I saw it done about a year ago. I should have rehearsed it properly. I bought the balloons this afternoon. So the moral of the story, assuming it does work, is of course that you should never beam down to a planet in a red shirt. That's the end.